Hello, good morning SH2 students. Today I'm going to tell you about count rate and also the decay graph equations. Okay, before we go to what is count rate, I want to show you first about these measurement things in physics lab, what we call as the Geiger counter. The Geiger counter is an apparatus to measure the count rate of a radioactive decay. So usually this Geiger counter is put in a room, so the radiations of the radioactive elements will not go out and can be harmful to the observer. So previously, when I am using this Geiger counter, the Geiger counter in my university, usually we will see the radioactive elements, from the other room. They will give us like a full of glass room, and then after that this Geiger counter and also the radioactive elements will be put in that room. The Geiger counter cannot be put far away from the radioactive elements. Why? Because even though it is put near the elements, it cannot count the activity, the exact activity of the elements, of the radioactive elements. As you can see from your textbook, although we are often interested in finding the activity of a sample of radioactive material, we cannot usually measure this directly. This is because we cannot easily detect all of the radiation emitted. When we put the Geiger counter, let's say, in front of the radioactive materials, and then after that, these radioactive materials will not only decay to the way of we put the Geiger counter. Of course, it will decay randomly. Okay, it will decay randomly, and then after that, it will spread not only to the way we put the Geiger counter. That's why this Geiger counter cannot measure all the radiation emitted. A GM2, or the Geiger counter that I mentioned to you just now, placed in front of radioactive source therefore only detects a fraction of the radioactivity, not all the activity. The further it is from the source, the smaller the count rate. That's why I'm telling you just now it needs to be put near the radioactive elements. Therefore, our measurements give a resistive count rate R that is significantly lower than the activity of the radioactive elements itself. Now, if we know how efficient our detecting system is, we can deduce A from R. So if we know the efficiency of our Geiger counter, then we can deduce A, we can determine the activity from the count rate. If the level of background radiation is significant, then it must be subtracted to give the correct count rate. Okay, let's continue. That is for the count rate of a radioactive element. Now, next, decay graph and equations. The activity of radioactive substances gradually diminish as time goes by. This thing I've mentioned to you before. The atomic nuclei emit radiation and become different substances. Of course, it will become the daughter nuclei, right? The pattern of radioactive decay is an example of a very important pattern found in many different situations. This pattern called exponential decay. So the decay of radioactive element is going down exponentially, as you can see from the graph. This is the graph of some radioactive materials. What we can see here is each of the radioactive materials will exponentially decay, decreasing. The tree graph, of course, looks different. They all have something in common: their shape. They are curved lines having a special property. If you know what is meant by the half-life of a radioisotope, then you will understand what is special about the shape of this curve. So what is actually the half-life, or T-half, of a radioisotope is the mean time, the average time taken for half of the active nuclei in a sample to decay. Half of the active nuclei in a sample to decay. In a time equal to 1 half-life, the activity of the sample will also be halved. This is because activity is proportional to the number of undecayed nuclei. It takes the same amount of time again for half of the remainder of the nuclei to decay, and a third half-life for half of the new remainder to decay. In principle, the graph never reaches zero. It just gets closer and closer to zero. In practice, with only a few undecayed nuclei remain, the graph will cease to be a smooth curve because of the random nature of the decay, and it will eventually reach zero, as you can see here. Yeah. The percentage of undecayed nuclei with the half-life of radioactive elements. At the beginning, the percentage is 100%. And then after that, after half-life, then it will reach 50, because half of 100 is 50. And then after there are 50% of undecayed nuclei, then it will go down again exponentially. It means from 50 to 25 after another half-life. From 25% of undecayed nuclei, it will go down again after another half-life, become 12.5, and so on. So all the radioactive elements will follow this kind of curve. It means what? It means that the radioactive elements will decay exponentially. So how to write it mathematically so we can find the exact amount of the undecayed nuclei after half-life? So this is the formula that you need to remember. N is equal to N0 times E to the power of negative lambda times T. N is the number of undecayed nuclei, and 0 is the initial number of undecayed nuclei, E is the exponential, and then lambda is the decay constant, and T is the time. In this equation, lambda is the decay constant, as I've mentioned to you. Note that you must take care with this unit. If lambda is in per second, then the time must also be in second. The symbol E represents the number E, the exponential, 2.71828. So when you do the counting, at least you take these 6 numbers or 5 significant figures. A spatial number in the same way that pi is a spatial number. So E, remember, 2.71828. You will need to be able to use the E to the power of x key on your calculator to solve problems involving E. Okay, you can use calculator for this one, of course. The activity A of a sample is proportional to the number of undecayed nuclei. Hence, the activity of the sample decreases exponentially. So if this is the number of undecayed nuclei, and then this is the formula for the activity. A is A0 times E to the power of lambda times T. Okay, so this is the example of arrangement of Geiger counter in lab. So this kind of experiment cannot be done by high school students actually, because when I was in college also, the one that do it is our lecturer, because this one is quite dangerous. Radioactive element is quite dangerous. Now let's see the worked examples. Number 7. Suppose we start an experiment with 1 times 10 to the power 15 undecayed nuclei of an isotope for which lambda is equal to 0.02 per second. Determine the number of undecayed nuclei after 20 seconds. In this case, we have N0. Remember, N0 is the initial number of undecayed nuclei. And then lambda is the decay constant and T is the time. You just need to put in all this to your calculator, scientific calculator, of course. And then you will get the N, the number of undecayed nuclei after 20 seconds is 6.7 times 10 to the power 14. So you see here that the number of the undecayed nuclei is decreasing because some of it already decaying. Next, a sample initially contains 1000 undecayed nuclei of an isotope whose decay constant lambda is equal to 0.1 per minute. Draw a graph to show how the sample will decay over a period of 10 minutes. So if the unit of time that both in minutes, then you don't have to change it. We have initial undecayed nuclei 1000 and lambda 0.1 per minute. Hence, we can write the equation for this decay. Okay, the N 1000 times E to the power of 0.1 times T. We can calculate the values of the number N of the undecayed nuclei at intervals of 1 minute. Okay, so this one, 1 minute, 2 minute, 3 minute, 4 minute, 5 minute. And then you count the N by calculator, of course, this one. And then 6 minutes, 7 minutes, 8 minutes, 9 minutes, 10 minutes. And then the number of undecayed nuclei. As we make it into a graph, yeah, from 1 minute to 2 minutes to 3 minutes, then it will goes like this. Exponentially decay. So that's all about how to count the number of undecayed nuclei if we know the half-life of radioactive materials. That's all for today. There is no assignment for today. The assignment will be tomorrow. Thank you for watching. You can reread again your textbook so you can be more understand about these materials. And then, of course, I am waiting for your questions to my personal way up. Thank you and bye-bye.